So, how do we experience the shape of a car? Well, we can touch it. So if I were to move my hand along the top of the car, I would feel the change in direction. And that's what we understand by these normal directions. They show how the surface is changing. And those surface normals don't change as we tumble the view. They're a constant property of the surfaces. But another way we experience the car is visually. So in real life, a car would be in an environment. So I've created some simple blocks here that could represent buildings, lampposts, sidewalks, etc. And in real life, you'd see these reflected in the shiny car paint. But we can't calculate those reflections with the hardware shading. So I've set up some views here, and instead I'm going to use the Direct Render tool, which I haven't taught you, but I want to use here because it uses ray tracing to calculate how the real reflections work from those simple surroundings that I created. So for example, you can see that the red block is reflected as a fairly straight line across the side window. But now if I change the view and re-render, then the red line has dropped off the side glass and I can see it here on the two wheel arches. And then if I change the view again to more of a side view and re-render, then the red line's not hitting the window at all and it's now across the body and the wheel arches in this continuous line. So the point is that our experience of the surface normals with our eyes changes as our viewpoint changes. So let's turn those surroundings off and have a look at the evaluation tools that work with these kinds of reflections. And the first one is the zebra stripes, which you've probably used already. And here, as I change the view, you can see that the stripes are moving across the surfaces. Now the zebra stripes are great for spotting continuity problems between surfaces. So here at the front we can clearly see a tangent break. And there's a G2 break across here. And probably a bit of a G3 break across there. Now over here on the diagnostic shade panel we've got the controls for the stripes. So I can switch this to being a vertical stripe to catch a particular piece of geometry that I want to evaluate maybe. But you can also see one of the disadvantages of the reflection analysis, which is that it's not consistent across the two halves, so I can't really compare one side to the other. We have a second reflection tool called a light tunnel, and this creates a cylinder of strip lights that we can actually see in the scene. And again we've got controls down here, so I can show the manipulator, which lets me move the actual tunnel in space. And I can change the number of bands, and I can turn off the display of the tunnel too. And again, as I tumble the view, you can see that the reflected stripes move across the surfaces. So why have we got the two tools? Well, to explain that, I'm going to turn off the car and just use a simple cube and a sphere. So if I apply the light tunnel first, you can see that on the side of this cube I'm getting consistent horizontal reflections. So it's as if that light tunnel is really there and you're seeing the real reflections. And then in the sphere I'm getting this distorted view at the end, which again is what would happen in a studio under a tunnel of lights. So it's giving us an idea of how the real life reflections would behave. But if I do the same with the zebra stripes, and I'll just switch those to horizontal, and I'll give myself a few extra stripes, then on this cube here the reflections aren't horizontal. So we're not really sure what we're reflecting, so it doesn't easily relate to a real-world situation. But if I reduce the stripes again and take a look at the sphere, then you can see the advantage of the zebra stripes, which is that I'm seeing a reasonable set of stripes anywhere that I want to look at it, with just a slight distortion around the edge. So I don't have that converging point that I had with the light tunnel. So when I'm building surfaces, the zebra stripes are the quickest and easiest way to look for continuity breaks between the surfaces. But if I want to understand how my car will look in the street with real-life reflections, then I'd use the light tunnel. So for example, up here at the top, I can see how the reflection relates to the top line of the window, or here how it rolls off the cantrail. So those two methods measure the surface normals with respect to a viewpoint. So we rely on moving the view to position the reflections. But there's a second method which uses a fixed direction vector to measure the normals. And this is independent of the view, which has some advantages. So the first tool I'll show you that does this is the ISO angle. And you'll notice that this time the reflection line isn't moving across the surfaces as I move the view. It's fixed in position on the car. And that's because it's simply calculating the normals in relation to a direction vector, which I can display by clicking on Show Manipulator, and then modify by clicking and dragging on these arcs. Now that was slow to update because I've got such a tight tolerance. So I can change that and then it moves across the surface more easily. So when I've got it in position, I can then tighten up the tolerance again to get a smooth line, which I can view and analyze and maybe move a little bit more. And I've also got the option down here of creating visual curves, which you can just about see here on either side of the white stripe in blue. Or I can create them as actual curves on surface, which you'll be able to see better when I take the shading off. And here I now have them as actual curves on surface. And these aren't on the tessellated surface, but on the smooth NURBS data, so they'll be very accurate. So I'll put the shading back on and I'll delete the curves. And now if I want this to look a bit more like the zebra stripes, then I can ask for multiple bands, and then choose how many. And what's interesting is that if I now go into the front view, I can compare the two halves. So I'll just switch the vector to the Y direction. And now you can see that the left and the right are accurate mirror images. And it's this consistency that makes this tool so useful. And finally we have another tool which is doing a similar calculation, which is called Isophote. And again it's fixed on the surface by default and independent of the view. So we can change the number of lines and change the vector direction to X, Y or Z direction. And in fact with this tool we can also switch to the view direction, which makes it behave again more like the reflection stripes. So the main advantage of the ISO angle and the isophotes is that we can create a repeatable, comparable analysis of the surface form. But in practice we'll make use of all of these methods to examine different qualities of the surfacing at different times. But don't forget that all of these methods rely on the tessellation tolerance. So if that's very coarse, then it will affect the display. And this will also apply to the cross-section tool, which I'm going to look at in the next tutorial.